Today we'll be talking about the Crazyflie test stand software. To begin with, what is the test stand? The test stand is the physical structure you see here in the top image and is used to restrict the Crazyflie's range of motion, so you can test out different controllers in a controlled environment where you won't harm the quadcopter. The test stand provides data about the angular position and angular rate of the Crazyflie, and it can be positioned to either measure stuff in the yaw direction or the roller pitch. It's used as a second stream of data to validate the Crazyflie's onboard IMU data and validate that it is performing as expected. Here's a high-level overview of the test stand system. On the physical test stand, there's an encoder, which gives back a voltage level between 0 and 5 volts based on the position of the quadcopter. It's connected using a custom cable to a test stand control board that was designed by a prior MicroCart team. The control board consists of an Arduino Nano and a button to allow for user input. The board is then connected to a PCB using a USB cable where it can then stream back data to the PC to be used by the host. Now that you have a high-level overview of the test stand system, we'll take a closer look at what code is running on the Arduino Nano on the test stand control board. When the Arduino is first powered on, the first thing that happens is it runs through a setup. The setup is where we put our initialization code, such as beginning serial, configuring the different pins for their purposes. For our case, we also get a home position so that wherever the quadcopter is when we start is the new 0 point for us. This is offset to a middle value because we want the range of values to go from positive 180 degrees to negative 180 degrees. We then take some measurements for data for the different rate calculations. And then based on the mode, we either turn on or off the LED. Lastly, we start a moving average object called myRate. This averages out the last 10 values from the rate measurement, since the rate can often have a lot of noise. After the setup, we move into the main loop. This is the loop that will be cycled through for the rest of the Arduino's operation. The first thing we do is grab the current time in microseconds, and then we take a current reading on the position of the quadcopter. The position of the quadcopter is going to be represented by a voltage level coming back from the encoder between 0 volts and 5 volts. This is sampled through a 10-bit ADC on board the Nano, and will return a value between 0 and 1023 based on the voltage level it receives. This corresponds to a clockwise increase in rotation around the test stand, as shown in the image on the bottom. Because the encoder won't be aligned the same way on every single test stand, and the quadcopter might start at a different position than what we have as 0, it's important for us to be able to adjust our home position so that our 0 can line up with the quadcopters. However, we don't want the difference between our current reading and our home position to be a negative number, so we add the maximum value and then do a modulation to get a relative position. Next, we move into handling the button press. The button allows the user to switch from rate mode to position mode and zero out our home position. The difference is between a long press and a short press. In the handle buttons, the first thing we look for on the button is whether it is high or low. If the button is high, this represents the button being pressed down. Once the button is pressed down, we start a timer in milliseconds. We then enter a while loop while the button is pressed. It is okay for this to be blocking since we likely don't care about the data during this time. Once the button is released, we move on and see how long the button was pressed for. If it is greater than what signifies a long press, which is a threshold of 1/4 of a second, we toggle what mode it is between position mode or rate mode. Otherwise, if it is a short press and is less than 1/4 second, we grab the current position and reset this as our home position, our new 0. Lastly, we switch the LED on or off dependent on the mode. The next step in the main loop is the position mode. The position mode takes the ADC value and scales it from 0 to 360 degrees using this 10-bit scalar value. We then normalize the value to make sure that it's between 0 and 360 degrees before we minus 180 degrees, giving us that range from minus 180 degrees to 180. Then, If we are currently streaming data and it is in rate mode, we send that position value back to the PC. Afterwards, we next go into the rate mode. In the rate mode, we must calculate the rate. In order to tell what the rate is, we must measure the change in position and the change in time. This can be done by taking the current values minus the previous values. We then normalize the change in position. Since crossing from the 0 point to 356 could look like a massive change, but really it's only a change of 1 degrees. Afterwards, we enter our most recent value into the moving average, my rate, and then get the latest average. If we are currently streaming and it is in rate mode, we then output that value to the PC. The final function in the main loop is handling serial commands. The serial interface allows the ability for the PC to send commands to control the test stand control board rather than using the button. A list of commands is shown on the top right. A similar structure is used in the code. When the amount of serial bytes available is greater than 1, we search for the @ sign, which signifies the begin of a command. We then read the following char, which represents which command we want. We then enter a switch case going through the different possibilities, and then execute the command based on the received one. The only command with a payload is the wait time command. This requires the @ sign to be sent first, then a W, and then an integer value, followed by an exclamation point. This allows the user to adjust the wait time between cycles to establish whatever frequency is best for the user. We then reset the variables needed for next cycle by recording the current time as the last time and the current reading as the last reading. We then enter a delay dependent on the time step. It's important to consider that the code could have been changed since this video. So while this video gives a high-level overview of the total system, it is important to check the most recent code to evaluate any changes before you begin.